Yeah, so actually I actually reduced my target integrity is very small, like 0.2. And so actually, so here is the order of our plan from here. It sounds like what actually you guys meant here is everything is the low redshift under the CMB, but I just talk about some of what we can do here. It's not actually some of well organized some of well, I just some of the sketch what I'm thinking, what is actually valuable here or something like that. So here actually this is actually some of the one of some specific program from the DESI. They actually targeting some of the LRG and the ELG in the high redshift. We actually scanning throughout the 14,000 square degree. It's a dark time. In the bright time, we can actually observe some of the local universe. So the new plan is that I was blanked before. But in the dark time, actually they estimate, okay, so although it's our local universe, and we are able to observe the several millions of galaxies from the very some of the faint to the bright. So probably the most interesting target or the science goal here is the more like astronomical, not the cosmology. But we are actually given something, so probably we could consider something what is useful for the cosmology. The size is here. It's a kind of the several megaparsec cubic here. And then the most interesting like the big science, dark energy or modifying gravity, or what is the universe is coming from the initial condition. The most some of the answer is to be known here. So it's not quite makes sense. We actually expect something much better than the outside the universe. So whatever actually we imagine here, probably is a confirmation because error is huge, but it's nothing new. But still, despite this factor, this can be a very some valuable information because the most precise information coming beyond our local universe, all over the place. That is actually something as a universe come from. And then probably the question is that how particular universe we are sitting is kind of some different some question we should address. So probably some of the key point here is that whether we are actually sitting in the local universe, whether it's consistent with all other part of the universe in the precision. So that actually what I meant by some of the cosmology in the low redshift in the local universe. So then we have to figure out what is the limit. So how much accuracy we need, and from which part, and we actually said, okay, so here is our limit, so we provide the information. So the guideline can be some of the recent progress of the recent complete the astronomical determination using some of the distance letter and the H0 the measurement, and also in the far outside the beyond the horizon. Nearly horizon, the CMB and the measure something, and the BAO and plus RSD, they provide some of the information of the H0. We know that actually we haven't found nothing wrong and this determination. And then there are many some papers published and then confirmation and including more data and then which is absent from the original one, but there is no change at all. Still, it's quite confirming. We also know that from the information of the CMB Planck and the BAO RSD, the both or every some of the observation, there is nothing wrong. So some actually people suggest we actually live in the huge void of the universe, but actually some they argue that is too much the small probability of the beyond. So we don't know any answer, but I just say this actually discrepancy can be useful for our estimation how much we need to achieve from the given condition. So now we understand very well of the linear structure of the power spectrum, and then we actually assume the DESI actually covering the north hemisphere and some point because it's a local universe. In the southern hemisphere, probably we do something. So in near future and also SPRX, they actually, at least in the local universe, in the high precision, they provide very precise information of the location of the galaxy. So probably in the near future, and we can also full the sphere of the scanning of the local universe, and then end with this red plot is that assuming the physical value of this, and then with the mode up to the Kmax, and then everything is blown up, and then there's no the information coming out. Now, because although we actually the observational effort and covered everything, and then there is no mode is available, so the direction we can go through is non-linear. So how far we can go, and from that point, and how much we can reduce the tether is the complete or not. So let me actually briefly describe the understanding of the large scale structure in the scene from the redshift space, and the facing and the major the difficulty. And the first one, before we go to the non-linear, and we don't quite understand the power spectrum, the large scale structure in the real space. And when the real space large scale, the mapping to the redshift, and there are some of the high order polynomial comes into play, we also do not quite know the framework effect. So we actually analyze those very carefully, and we actually suggest the realistic non-linear bounds. The first one, before we go to the redshift space and the large scale structure, then how much we understand the theoretical model of the large scale structure. You see this is from the trustable bound, and then the simulation measurement is go beyond this, and then the most recent progress of the perturbation theory is well matching. Going beyond 0.2, there is only marginal difference, but actually those actually some of the difference by the 5 or 10%. So theoretical the prediction a little bit short of, but we have the simulation. We can actually suggest some of the semi-analytic model. We actually derive some of the residual between the theoretical prediction with the embodied simulation, and we can actually estimate some of the lowest the order of the growth functions, the structure. So with only one simulation, probably we can predict some of the nonlinear structure. Or now actually people the interest in the emulator. Eventually this is just a 2.4 as a function. So we can make the emulator the approach. Anyway, although this is not complete, and we are able to predict the nonlinear correction term, so it does not actually provide any solid nonlinear bound. But in my opinion, probably some of the nonlinear bound is coming from the mapping. The second part, in the higher order polynomial, and then there is a series of the small order to the high order. Something different from the previous one is that still in the nonlinear correction term was just 2 points, but here as we go the higher and the higher, which produced the squeezed bispectrum and the squeezed trispectrum. And we actually stop here. If you go in the next term, probably you encounter like 5 or 6 correlation functions. So difficulty was something different from the what we experienced. How much time do I have? So we actually found the residual test, and we discover from the basics of the second order, and as we go beyond k equal the 0.16, it starts from the showing some possible contribution in the high order. So basically, I set this bound based on our incomplete analysis of the mapping. The second one is that the FOG term. Figure got up to the k equal to 0.06, and the Gaussian is dominating. And eventually, when you go higher, we need to introduce a new parameter. So this is actually conceptual, and as you go into some of the full nonlinear scale, but with more parameter, eventually constrain possibly the blown. So in that sense, I set the bound of our understanding Kmax from the 0.1, and we actually set the bound 0.16. Now actually we actually set the limit of the estimated determination of distance ladder from the cosmological parameter. So from this point we can say something, but for like some of the critical observation, nobody trusts 90% or 95%. We need to increase the constraint as the higher. So probably some of with given some of the limit, and we can actually consider some of the combination of the power spectrum and the power spectrum. But this is still so only. It's not a separate the sky, and the power bispectrum is coming from the same patch of the sky. So probably there is some significant amount of the cross correlation in the covariance matrix. So offset should be carefully counted. So our model is that in the bispectrum, and we don't make any specific squeeze limit or the triangle. We actually count everything. So in the bispectrum, in the redshift space, distance between the R1, R2, R3, and there are two more degrees of freedom. The angle from the redshift, so it's coming to the 5 coordinate. Signal to noise of each mode is really small, but eventually if you actually count the huge number of the modes, eventually the signal to noise of the power spectrum and the bispectrum really is equivalent. So we can expect some similar power of the constraint, whatever we want to understand. But it is a little bit degraded by some of the cross covariance, and we actually count those very carefully. So from the power spectrum only constraint up to our knowledgeable nonlinear structure, and we get into here. So if in the future, and the astronomical measurement still stay here, and then cosmological determination from the outside the universe still stay here, and if we can actually provide the information with this error range, then probably it actually say some information. So I actually summarize my talk with the one single slide. For the power spectrum, we can do it, and then for the bispectrum, still it's a very challengeable. Basically, it's something different from the power spectrum in the RSD and the redshift space. The bispectrum is still. In the Kaiser term in the power spectrum, and then correction term from the higher polynomial, it's quite a huge next order. But in the bispectrum structure, something like that. Kaiser term is coming from next order, and also the higher the polynomial is also next order. So if you collect some redshift effect, then we have to count every term. But actually, I pay attention of this squeeze limit of the bispectra. And from our experience in the past spectrum, it can be very significant. But something is a bad sign is that actually comes is not next order, but that actually comes in first order the correction. So to summarize this, and then in the high nonlinear design, paper opens 1.6, it will really changeable. So if we want to go ahead, so although data is coming in our tables, and we have to discuss among the community that whether this the local peculiarity of the information or our local universe is valuable, and then considering all the threat we actually need to provide in the future, and then the people really keen to know what is actually cosmology in our local universe. As far as we stay in the interest and we wait for the result, I just show there is still way, although it's very difficult, and we can access those information, and then we can provide peculiarity of the local universe against some of the outside world.